All right, ladies and gentlemen, welcome back to another video. We're going to keep you guys moving along. We talked about section 9.4 yesterday. We're going to talk about section 9.5 today, which does a little bit more with calculus. We did a derivative of polar equation. Now we should also talk about area and finding arc length. So this will be the last section with polar, but there definitely are some questions here that take a little bit longer, so we should definitely mention them. So how about another warm-up, just like we've done in the last several videos. So if you can pause it, everybody can take a chance. Do you remember how to find the arc length in rectangular? So can you find the arc length? So it says here, it says, can you find the length of the graph of y equals sine of root x? The length of the graph is the arc length. So pause the video, take a second. Which one? Which one of these choices are you going with? All right, in terms of solution, I was hoping that you picked letter D. Again, the setup or the formula to find arc length in rectangular is to set up an integral, the integral from a to b of the square root of 1 plus f prime squared. So in this case, you'd have to take a derivative of the y equals sine of root x. Hopefully you'd agree if that we take a derivative of sine of root x, we're going to run into chain rule. So I have built the chain rule off to the side here. I find out what y prime is, and is if you take that and dump it into the integral of the square root of 1 plus f prime, you will end up with letter choice D. Feel free to pause the video if you need it. In our last video, we talked about section 9.4, polar graphs and polar coordinates. We talked about polar coordinates being another way that you can represent coordinates that we know in the rectangular system. We know that polar is built on r and theta, r being the distance from the origin, how far do you need to travel, and theta being in which direction do you need to travel. So we talked about converting. We said that there were kind of like these 2 or 4 maybe equations you could use. We know x is dependent on cosine and y is dependent on sine. We know tangent of theta is y over x because of opposite over adjacent. And we know the classic equation for a circle, x squared plus y squared is equal to r squared. All right, we did talk about technology, being able to graph on the graphing calculators with polar. Again, you just have to switch over the mode to polar, and then instead of on your y equals screen, you'd see y equals, you would now see r equals, which would be a good indicator that you're graphing in polar. We know there's some different types of graphs in polar. We have propellers, we have leaves, or these kind of shapes. We have the Archimedean spiral. We have circles, cardioids, limisones. So these are things that we'll see a little bit more of today. And last but not least, the last thing we kind of touched on is how do you find the slope in polar? Well, you'll take the derivative of the y component with respect to theta, divide it by the derivative of the x component with respect to theta. And again, we said yesterday, don't worry about the crazy formula. Instead, just think about x being r cosine and y being equal to r sine. And we know that if we're going to try to take the derivative, we're going to run into product rule, and that would be a good way to remember it instead of having to memorize that symbol for symbol. I would say it'd be easier to think about it that way, and then just build the product rule since all of you are pretty strong with product rule back from first semester. So section 9.5, the last section that deals with polar. Again, it's kind of quick, but this one we should spend a little bit more time on. If we can talk about the derivative, we can talk about the slope, then we should also be able to talk about area and arc length. That just kind of screams calculus, where the slope is the derivative, the area would be the integral. So the first thing that we'll mention, or the book wants to mention, is this formula. So there is a formula, and it would have been first introduced to you in geometry. So in geometry, you would have seen the area of a sector of a circle. A sector of a circle is basically just like a slice of a circle. So imagine that you had like a pizza or a pie or something like that in the shape of a circle. If you started at the center and then cut out a slice of it, that slice would be a sector. So the area of that sector could actually be built with 1/2 theta times r squared. Again, r is going to be the distance from that center out to the circumference. And then theta is going to be the degree measure from where you're starting to where you're ending. So if this was going to be where I started, this is where I was ending, then theta would be how far did I have to travel in terms of measure, in radians or in degrees, from that starting slice to the ending slice. So that's not too much calculus, but how we can transform it into calculus is we can talk about little sections. We know that regular integrals are broken up with rectangles. Here, if we do things with a sector. For circles, it's not too bad because they're all going to come from the center and work their way out towards the circumference. But we can also do it for polar graphs or polar regions. But you'll see that if I start at the origin and work my way out towards the curve itself, it's not always going to be the same shape every single time. So what you're going to end up kind of creating are like these little triangles, and these triangles are going to have a height and a base. So in this case, if you wanted to, you could break it up in a similar fashion, kind of like what we did with rectangles when we were first finding about the integral and finding exact area under curves. But here, it wouldn't be so much rectangles, it would be triangles. So in a similar way, we could add those all up. You can see that there are some limits behind the scenes here, right? So the smaller of the thickness of the triangles that I work with, the smaller the error is going to be. And of course, that will be more towards an infinite number of triangles. So we know that limits usually something getting really big and something getting really small. So without further ado, the main point of where we go here is how do you find area in polar? It's just 1/2, and then kind of using that little formula that we know from geometry, or you should have seen. 1/2 theta times r squared. Here we have 1/2. We have the function squared because that's really what's going to take the place of r. So when we get equations like r equals in polar, that's going to be what the function in terms of theta is going to be. And then if you think about it, wherever we start alpha and wherever we end beta will tell you when to start collecting and when to finish collecting. So in this case, this would kind of be like your theta, right? So if we go back to this kind of formula, 1/2 is a coefficient that goes on the outside. We do see r squared here on the inside, but then what about this theta that's part of that geometric formula? Well, that's going to be built based on where are we starting and where are we ending our collection of area. That will tell us how big theta is going to be, and it will collect everything inside of there, which will give us the exact area. So it makes a lot of sense with the formula that we know. So for our examples today, we're just going to write the integrals, and then we're going to use the calculator to actually calculate them. This is a very common thing that you'll see on the AP test. There are not a ton of questions, but the few ones that do ask, usually you are allowed a calculator to find them, unless the calculations are really simple and it's really easy to determine what the values are in the unit circle. Okay, so first things first, example 1. Can we find the area of one petal of the rose curve given by r equals 3 cosine of 3 theta? So here we have r equals 3 cosine of 3 theta. We could also punch it into the calculator. If you have your calculator set into polar mode, you could actually graph this. So where would it start? Well, it's always going to start kind of like the unit circle, where theta is equal to 0. So the starting point for this one would actually be right here. How I know that is because that's the point that's on the positive x-axis. So if you wanted to identify that in your notes, you could say this is where it starts. It starts here. And then what I would be interested in is where is the first time that it actually goes back to the origin. So it turns out that on this curve, if we start here at the point 3, 0, is actually going to work its way back towards the origin. So I'd like to find out when was the first time that it actually got to the origin. So you could do this with the calculator, but it's actually not that hard to do by hand. Just take your equation, and you know the equation is r equals 3 cosine of 3 theta, where r is the distance from the origin. But if I want to find out when the curve is actually going through the origin, then what would that mean about r? That would mean that r is equal to 0. If you don't have any distance from the origin, then of course you must be on the origin itself. So what you can do is you can take r equals 3 cosine of 3 theta and set it equal to 0. And you can actually solve this for theta. So if you divide both sides by 3, that's not going to change 0 at all. You're going to get cosine of 3 theta is equal to 0. Where is cosine equal to 0? Well, on the unit circle, we know that cosine is equal to 0 at pi over 2 and also at 3 pi over 2. Another way to write 3 pi over 2 would be negative pi over 2. We know that traveling in the negative direction would be traveling clockwise, where traveling in the positive direction is traveling counterclockwise. So in this case, you could say cosine of 3 theta is equal to 0. Since cosine of 0 is all of these two places, then we know that this 3 theta is going to be equal to those two places where cosine was equal to 0. Again, this comes from pre-calculus and solving these trig equations. We can then divide both sides by 3. And if you do that, you will actually find out that theta is going to be pi over 6. That's pi over 2 divided by 3, and negative pi over 6. So if you think about it in terms of degrees, maybe that would also help. We know that pi is 180 degrees, so 180 divided by 6 is 30. And if you look at the picture here, this dashed line that we see here is kind of like 30 degrees. That would be your pi over 6. We also know that these petals are symmetrical. So if you look at this one here, you could say this one is negative pi over 6. It's the same distance from that positive kind of x-axis, but in the other direction. So this would be negative pi over 6. So if you wanted to find out the area of this petal, then you just use this little formula that we have. You could say the area is equal to 1/2, and then we'll go integral. Where should we start it? Well, the lower bound should be negative pi over 6. The upper bound should be regular pi over 6. And then we should have r squared in the integrand. So this will be the quantity of 3 cosine of 3 theta. And that quantity will be squared, and then d theta. So I'm kind of just using this equation that we have here, the 1/2. We did found the bounds for our petal, and then we just had to have the function in terms of theta squared inside of there. So now we could actually take this into the calculator and find out what this area is by using the integral feature. So if you do this, you can actually use the graphing calculator. So feel free to pause the video so everyone can get a chance to do it. And if you get a chance to do it, you should get an answer that is approximately 2.356. So in this case, it'd be my answer. There are a couple other ways that, I guess one other way that you could do it. You can also talk about it in terms of symmetry. If you know that the graph from 0 to pi over 6 will do the top part of this petal, then you could just multiply the integral by 2, which would cancel the 1/2 on the outside. Something else that's often asked is what's the area of all the petals? Well, if you know the area of this one petal that's kind of shaded here in pink, and you know the other two petals are going to be the same, then you could just multiply the result that you get by 3. So these are all kind of common questions that are often asked. So there's example 1. Feel free to pause the video if people want to talk about it. Again, I gave myself some extra space if we needed it. I didn't really need it for example 1, so let's keep rolling. How about example number 2? So here it says, find the area bounded by a single curve. And then here it says, find the area of the region lying between the inner and outer loops of the limacon, r equals 1 minus 2 sine of theta. And I should say this because it's come up in conversation in previous years, is do I have to know that the equation r equals 1 minus 2 sine is a limacon? No, it actually would be something that if you needed to, you could graph on the graphing calculator. Nobody would expect you to know just by looking at it that that's a limacon. So if you look at the picture, it would be kind of the same thing as if we graphed it on the calculator. We see this limacon, which is basically a cardioid with like another like teardrop loop here on the inside. So I would consider this to be like the little teardrop shape that's missing in terms of the area, where the area that we're interested in is going to be this area that's shaded here in pink. So I think that's a good way to kind of preliminary have an idea of what we're looking for. So first things first, where would we start? Well, we'd start on the positive x-axis, which means this would be kind of like my starting point. So I would like to know when is the first time that I go through the origin. So how could I find out the first time that I go through the origin? Well, of course, I could take the equation r equals 1 minus 2 sine of theta, and I can set it equal to 0. If I set it equal to 0, I can add the 2 sine over, so then it would become 1 is equal to 2 sine of theta. I could divide both sides by 2, and then I would get sine of theta is equal to 1/2. So I got to think to myself, on the unit circle, where is sine equal to 1/2? Well, sine is going to be equal to 1/2 at pi over 6. That's in quadrant 1. Also at 5 pi over 6, which is in quadrant 2. So these are my two values of theta. And if you look at the picture, you can see is exactly why this dotted line or dashed line is at the pi over 6. And then symmetrically, you also have it at 5 pi over 6. If you were to extend these lines, they would actually extend and give you kind of bounds on that little teardrop that's missing there on the inside, which the book is calling the inner loop. The outer loop would be described as like the entire pink region plus that missing teardrop. Like if nothing was missing, that would be considered like your outer loop, where the inner loop is just that teardrop shape that's missing right there. So that's a good place to start. At least we know that if we want to build this little teardrop, we could actually just graph from pi over 6 to 5 pi over 6. Now, if you guys want, this could actually be something that kind of helps, because sometimes the bounds for the integrals can be kind of tricky. Is if you want, you can actually pause the video here in a second. Take this guy into your graphing calculator. Take 1 minus 2 sine of theta into your graphing calculator. Hopefully you're in polar mode. And then hit window once you have that in there. And in window, now there should be an option for theta min and theta max. So maybe make this the first one, make this theta min. And then the second one, let's make this theta max. And then if you actually end up graphing it, you can zoom in a little bit and you'll see that it will actually only graph that little teardrop for you. Now, if you do a regular zoom 6, it's going to be kind of small. But if you change the window so that you have this theta min and theta max, you can actually zoom in and you'll see that this will actually just by itself graph that little teardrop shape. So what we need to do is try to find this area of the whole entire thing and then subtract away this little teardrop that's missing. So I'm going to use another little slide so I have some extra space. The first part's actually not bad. We've kind of already figured out how could we find this inner loop. So the inner loop, we could find the area with our formula. We know the formula starts with a half. We have an integral. Where should we start the integral? Well, we should start it at pi over 6. That's in quadrant 1. Where should we stop it? We should stop it at 5 pi over 6, which is in quadrant 2. You should then take r, which is 1 minus 2 sine of theta. You should take that quantity, square it, and then d theta. So if you want, you can take a second into your calculator. What's this going to come back as? Feel free to pause the video so everybody can try. All right, I was hoping you got something like 0.544. This is what I got in my graphing calculator, so that would be like the interloop. So I know that as soon as I get to 5 pi over 6, now this actually starts drawing the outer loop, so kind of going outwards this way. So then if we go all the way to 2 pi, then that's actually going to collect all of this area, but then at 2 pi, it's actually going to stop short here. And then notice the only part that we're missing is this tiny sliver that was going from 0 to pi over 6. So instead of having to write two integrals, which is, there's nothing wrong with that. I mean, it would get you the same thing as if we went from 0 to pi over 6 and then added from 5 pi over 6 all the way to 2 pi. We actually could just go from 5 pi over 6. So that's going to be where we stop drawing this little teardrop shape. So if I go from 5 pi over 6, that's going to give me all this. And then what I can do is actually just go pi over 6 past 2 pi. So what is 2 pi plus pi over 6? Well, if you want, you could find common denominators. You can hit with a foo. So this would be 12 pi over 6 plus another pi over 6, which is 13 pi over 6. So if you want, you can do the same thing in your graphing calculator. If you want to get a little visualization for it, feel free. You probably already have this in your r equals, the 1 minus 2 sine theta. But now instead of the theta min being pi over 6, let's change the theta min to 5 pi over 6. So let's start it here at 5 pi over 6. And then for theta max, change the theta max to 13 pi over 6. And if you do that, you'll actually see that it will build the entire outer loop for you. So in this case, let's say the outer loop, we can find its area. We can start with a half. Well, where do we have to start it? We have to start it at 5 pi over 6. And then where could we take it? We can take it to 13 pi over 6. And of course, it's 1 minus 2 sine theta. And then square the entire quantity. Feel free to take it into your calculator if you want to pause the video again. If you want to take my word for it, you'll have 8.881. So 8.881 would actually be this entire region, which would include the teardrop. But if we were just trying to find this pink region, hopefully you'd agree, we just need to take this outer loop and subtract away this inner loop. So in this case, I think our final answer is going to be to take this 8.881. I could probably do that a little bit better. So 8.881. And then we're going to subtract 0.544. And if you do this on your calculator, we should get a final answer, something like 8.337, something like this. So So I think it helps. I think the graphing calculator helps to kind of visualize what's happening. I think these can be kind of tricky if you don't have somebody like me leading the example. If you're on your own, you kind of need to find out which region are you interested in. Basically, try to find out on the polar graph, when do you start drawing the shape that you're interested in finding the area of, and when do you stop? That would actually tell you the bounds. Where should you begin the integral, and where should you end the integral? Okay, so I think that does a nice job with example 2, in my opinion. All right, so then it is possible to have multiple polar graphs at the same time. So how do you find points of intersection? Well, just like you would in rectangular, if you have two equations, you're trying to find out where they intersect each other. You can set them equal to each other and then solve for x. In this case, if we have polar graphs, we know that polar equations are in terms of theta, so you can set them equal to each other and solve for theta. Whatever value of theta you get when you solve would have to be the value of theta where the two graphs intersect. So they give us an example. If we had these two, we could set them equal to each other, we could solve. We would have to know some things about the unit circle, and then we could solve for theta. Whatever we get for theta would be the intersection values. So how about for example 3? In example 3, we are trying to find the area of the pink region here. But the colors are kind of helpful because they help us determine which region's which. You'll see that on my picture here, which you obviously don't have on yours since yours is in black and white. We have this pink region, and then we have this kind of like little sliver of a gray region. So what we'd be interested in finding is this pink region here. So let's see if we could do it. So maybe the first thing we should do is highlight the two functions. We have a cardioid. You can see that's kind of like in lighter gray. And then of course in a darker black, we have a circle. So a couple things that I can already say about the two graphs. If you look at the cardioid, it does start at 0 and then work its way all the way around to 2 pi. So for the cardioid, we know that it goes from 0 to 2 pi. But then how about for the circle? Notice the circle does not go to the right of the y-axis. So that means it actually starts at pi over 2 and then works its way around the circle, but it never goes to the right of the y-axis, so it actually would end at 3 pi over 2. So that's something to consider if we need it. That could be something. So we would like to try to find out, maybe first things first, find these areas. We know there's going to be a little bit of overlap. So let's see maybe if we can find this first little gray sliver here. In order to do it, we would have to find out where do these two graphs intersect. Well, they intersect here at the origin, so we can definitely see that 0 is one of those intersections. But then we should also find out the second intersection right here. How we can do it is we can look at the picture, which is very helpful. But if we don't have a picture, we can actually just do a little bit of algebra. So let's go for it. So the algebra would say, take these two equations, set them equal to each other. Since they're both equal to r, set these two parts equal to each other. So how about -6 cosine of theta? This is equal to 2 minus 2 cosine of theta. Let's start solving. So just add 2 cosine of theta to both sides. If you do this, you're going to get -4 cosine of theta is equal to 2. Divide both sides by -4. This would mean that cosine of theta is equal to -1/2. So then you have to think to yourself on the unit circle, where is cosine equal to -1/2? Give you a second. About 2 pi over 3 and 4 pi over 3. So in this case, we have two spots. So these would be my values of theta. If you look at your picture, you'll see 2 pi over 3 is in quadrant 2, which makes a lot of sense since the circle doesn't go in quadrant 1 or quadrant 4. It should start, the first intersection point should be in quadrant 2. There should also be an intersection in quadrant 3. And if you look at it, that's the 4 pi over 3, these dashed lines that you see kind of on your picture. So that'll be very helpful. If you take the two functions, set them equal to each other and solve, that would kind of tell you some nice things in terms of bounds. So what if I want to find this little gray sliver? Well, I know that the gray sliver is entirely dependent on the circle. Notice it doesn't go all the way out to the cardioid. It kind of stops here on the dark black line for the circle. So maybe what I can do is slide down and give myself a little bit more space. So what about if we said to find this little gray sliver here, then let's say we're doing it with the circle. We know that the formula for area and polar is going to start with a 1/2. We have an integral. Well, where is it going to start? It starts right here. That's at pi over 2. So in this case, we could say start this guy at pi over 2. Then where should we stop? Well, we should stop at the intersection point of 2 pi over 3. And then the function for the circle is this -6 cosine of theta. Of course, we need r to be squared and then d theta. You can take this into your calculator. And feel free to pause if people want to do it, or if you want to take my word for it. This is going to be 0.815. So that would give me this region right here, this little kind of a gray sliver. Now what if I wanted to find this entire region for the pink region? So then if I was going to do this for the pink region, in terms of the cardioids, I would have to start it right here at 2 pi over 3. That's going to be the intersection that I found. And then where would I stop it? Well, it looks like it stops here on the negative x-axis. So then where do you think on the unit circle? Using your knowledge of the unit circle, where should we stop it? We're going to start it at 2 pi over 3, and we should end it at pi. We know that the negative x-axis is pi. So in this case, we could write it out. We could say, let's do it for the cardioid. We have a half. We're going to start the integral at 2 pi over 3. We're going to stop it at pi. And then we know the function itself is 2 minus 2 cosine of theta, and then quantity squared, d theta. You can take it into your calculator, or if you trust me, this is at 7.0 and then 39. So then how about the entire shaded region? Well, the entire shaded region would be like saying take this region that's in pink, and then we can add it to this little sliver of gray. So in this case, if we were going to do shaded entirely, not just the shaded pink, but also just shaded in general, we can say take the 0.815 and then add it to 7.039. And then in your calculator, we're looking for an answer like 7.8 and then 54. Okay, so not too bad. Again, the whole point here is to be able to write the integral and then use the calculator to actually calculate it for you. So again, if you were doing this one on your own and you had some ideas, you could definitely use the calculator, restrict the window so you can see which part of the graphs you're drawing and which values of theta, and I think that that's a really helpful way to do it. Okay, the last thing that we have for you is arc length in polar. So at this point now we have arc length in rectangular, which we saw in the warm-up, kind of on purpose. We have arc length in parametric, which we saw. And then last but not least, we have arc length in polar. So it does look familiar. It has an integral. It has a square root. But if we're doing things in polar, we have to start with the original function in terms of theta. So whatever r equals, we first have to square that. And then we're going to add it to the derivative of that function, also quantity squared. So it's not that bad. They also give us this as notation. Because we know that the function in terms of theta is r, we could do r squared plus dr d theta and then squared. So yes, this is another one that we're going to have to know, but this is the last one. So there are 3 different arc lengths, one for rectangular, one for parametric, one for polar. So let's see, could we write it? Well, the first things first is that they give us r, so we have a piece of the puzzle. We have a function in terms of theta, so the only other thing that we would need is the derivative, or dr d theta. We know the derivative of 2 with respect to theta is going to be 0 because it's a constant. What is the derivative of -2 cosine of theta with respect to theta? Well, I was hoping somebody said 2 sine of theta. Again, we know the derivative of cosine theta is negative sine. So because there is this -2 out front, that's going to get multiplied by the negative, which is going to turn into a positive 2 sine of theta. So then if we want the arc length, it's actually not that bad. We'll go integral. Here it's saying, can we find the arc length from 0 to 2 pi? So it's giving us the bounds. Again, there are no coefficients here like the 1/2. That's for area, not for arc length. And then what I would do if I was you is make a big old square roots. Inside of here, start with the function itself, which was 2 minus 2 cosine of theta, quantity squared, plus the derivative. The derivative was 2 sine of theta. We're going to square that quantity as well. And then, of course, d theta on the outsides. And just like the other ones that we've done with arc length, as soon as we can write the integral, the calculator can finish it. You might be kind of surprised by this one, like we did for the other ones. If you want to pause the video if people want to, that's totally fine. If not, then this one actually a little bit surprising. You would get a nice clean answer of 16. So if I go find the arc length for this guy, which is again the distance that I'm traveling around this graph, this cardioid, then we actually would get exactly 16, which is kind of interesting. So in this case, another version of arc length, but then luckily for us, the last version that we need to know. Okay, so there is a small assignment coming your way, and then a little bit of practice tomorrow and Thursday. And then after that, we'll move on to vectors, which is the last topic that we'll need to know. All right, guys, I hope the examples were helpful. Hopefully you got a chance to make sense of it. If not, feel free to watch the video again and try the practice and give it a chance. Feel free to use your calculator. That can definitely help with the graphing. I know that it's helped in years past. All right, guys, I will talk to you soon, and I'll see you in the next one. Have a good rest of your day.